So it's an honor to have Professor Ghosh here. He's a great expert on electrical properties of glass. He works for the Indian Association of Cultivation of Science. He's a fellow of the Indian National Academy of Science. He's the editor-in-chief of the Indian Journal of Physics, which, by the way, was founded by Raman.
Yeah.
So he'll tell some stories, extra stories about Raman. So this could be called the Raman School of Advanced Glasses and Glass Ceramics. He is a Marie Curie Fellow also.
Yeah.
He has received many awards, and he is very, very well known in the field of electrical properties of glass. So, Professor Ghosh, it's my honor to have you here.
Thank you for your kind introduction. Okay. Let me first introduce my institute here. There is the Indian Association for the Cultivation of Science, situated in the city of Kolkata in the eastern part of India. This institute is very old, 134 years old. On the last December 29th, we celebrated its 140th birth anniversary. And this institute comprises the 6 full departments and 4 units are executing basic research in diverse fields of physics, chemistry, and biology. And this city of Kolkata has a long heritage. It's the most cosmopolitan city, and this environment is very good for people living in different parts of India, and they gathered Kolkata and start living there because of its cosmopolitan nature. About the city, you can see the 5 pictures. There is 5 Nobel laureates who either worked in the city, Kolkata, or born in the city of Kolkata. First one, Sir Ronald Ross, he discovered parasite of malaria working in a medical college in India. So he got Nobel Prize in 1902 in physiology or medicine. And the second one is the Rabindranath Tagore. He is a very famous, he's known for his very famous song and for poetry as well as for essays. And he got Nobel Prize in 1913 for his work on a handful of songs. And the third one, which is very interesting, is Professor C.V. Raman, who got Nobel Prize in physics from our institute where I am working, from the Indian Association for the Cultivation of Science. Even he discovered Raman effect in that institute with a very simple equipment we cannot imagine. Nowadays, Professor have shown us some Raman equipment in his laboratory you have visited. And that is very sophisticated because of the development of electronics. But at that time, there is no such electronics. So sun ray was the source, passing through a hole in the wall. And his eye was the detector. Can you imagine? He was detecting the radiation with his eye. And he certainly found that a new radiation is coming from the source, from the grating, diffraction grating. He used prism to disperse the light and then pass through a liquid which scattered the light, the original light of same wavelength, and some new radiation. He termed it as a new radiation. And thereafter, people called this the Raman effect, because the new radiation have some wavelength which is different from the original radiation. Either its wavelength is longer, and some of these radiation have wavelength is shorter. And that was what is Raman effect. But he has a story I want to tell. Because after doing his graduation in Chennai, in the southern part of India, he took a job as an accountant officer in an accountant office. because the salary was very high. And he was posted in Kolkata. Then one day he was passing through a street, and he found the signboard of an institution that is written Indian Association for the Cultivation of Science. And he entered the institute and saw many people working there. He was very enthusiastic. And he started working after office hours. He did his office hour within the day and started working at night. Then he decided, he felt so interesting, he decided to leave the job with hefty salary. You cannot imagine this day. And join this institute with practically no salary for earning and living. His salary was so low, he was just earning for living. And due to his curiosity in science, at that time, there was in Calcutta a big university, Calcutta University, which is a famous university. The vice chancellor gave him a job of professorship in physics. He got salary from university, but worked in a separate institute which is not associated with this university. But he was not taking class, but he was a professor, and ultimately he discovered this Raman effect in 1930. He also first published this observation of new radiation, establishing a new journal called Indian Journal of Physics. And so this journal is also very long time. I am now presently the editor-in-chief of the journal. And its impact factor is also very high, 1.4. So you can think of publishing some of his articles in Professor Raman's journal. And there is one of the two Nobel laureates, Mother Teresa. He was, although a Polish citizen, but he took citizenship of India and worked in Kolkata and got Nobel Prize in 1978 for peace. And this is one, Professor Amartya Sen is still working in Kolkata, in somewhere. He got Nobel Prize in 1998 in economics. With these few words about our city, I would like to come back to my the main topics. I will first tell you about a brief introduction about glass, but this section has already been talked by many people, many lecturers here. But I will only pick up some of the points which will be necessary to explain the electrical conduction and ionic conduction in glass. These are the two main topics I will cover throughout my lecture. It has already been shown that this glass has no long-range structure as the crystal is. I have shown here because you can see the difference between the structure of crystal and glass. One thing, there is no drastic change. You can see that. If you pick up, this is practically the silica, two-dimensional picture. The silicon oxide surrounded by silicon surrounded by 3 oxygen here. You can, when it is in glassy state, you can see the same thing is happening. So there is no change in at least first coordination number. And this is the point I want to mention you. Another point is, which is important, is that the bond length and bond angle, which was valid in crystalline materials, is also valid in glassy state, but with some fluctuation of 10%, say, but not drastic change. This is one of the things which we consider in our future discussion. And another point is that the open space, that is space not occupied by atoms in crystalline state and in amorphous state or glassy state, that then the glassy state has more open structure. And this open structure provides us opportunity to functionalize glass in a different way. It can be made ionic, it can be made metallic also. An oxide glass can be functionalized as a metal. If you can imagine, if this structure was not there in glassy state open structure, we cannot generate this type of functionalities in these types of materials. Because this has been already discussed, you can see, first when you have a glass, we have to check it whether it is a glass or crystal. So there are two ways. One of the X-ray diffraction, we can get it very different X-ray diffraction pattern in XRD, as well as this is the modern technique for electron diffraction. You can here for crystals we can get a different spot. Each spot indicates a set of crystalline planes, whereas in glassy materials we can have a diffused ring. But I am sorry that figure is not clear. You can have a diffused circular rings without any spot, which indicates that the long range order of the materials. To describe electronic properties, I must state the electronic states of in disorder or in glassy states. Because when an electron is moving in a particular materials, then since electron is a quantum mechanical particle, so it can be described by the so-called wave function, quantum mechanical wave function, Schrödinger wave function. We can solve some Schrödinger equation. For crystalline materials, it is very easy because each atom can be represented by their atomic potentials, which are of same depth of and same space periodicity. If we solve Schrödinger equation, the consequence of is that it is a periodic function. This one, like that, called block function. So the psi naught r has a periodicity of the lattice, and this is an exponential function. There is actually three-dimensionally, it is there is a wave vector and the space vector, and is a dot product. And we can see that this function has the periodicity of the crystal. So it is well known. And if we can consider the same thing in glass, whether this type of picture is valid here or not. Because you can see for glassy state, we have positional disorder as well as disorder in the depth, the fluctuation of the potential well. So long time back, in probably 1958, P.W. Anderson was trying to find the solution of these questions for disorder materials. If you have a random lattice and you can inject an electron, and he asks whether we can have this electron after some time on the other end of the sample. Then he, after rigorous calculation, he showed that the answer is negative. For that, we can have electron everywhere in the metal or semiconductor in the materials, but here this is not the case. After solution, with some restriction in condition, you can see the fluctuations in the potential depth. If the fluctuation of the potential depth is small, then theoretically he has shown that the wave function of this electron can be represented by a function like that, psi equal to psi naught exponential minus alpha r. You can see here is the function is periodic for crystal, but here the function is non-periodic in crystal. That is, it cannot be propagating throughout the whole materials, but it is confined in a narrow region. I have shown here pictorially that the wave function is sinusoidal for crystalline materials, so that the probability of finding the electrons is everywhere unity. But here in glassy state, since the wave function is exponential, so the probability of finding the electron everywhere is not like this one, but it decreases with distance. And this phenomena is called localization, or more precisely, it is called Anderson localization. And for this discovery, for this prediction, he got Nobel Prize in maybe, I don't know the year, but around 1970 or something like that, along with Professor Mott, whose work I also describe in the next. And so, to describe the electronic states in glassy states, I have to compare it with the electronic states of the crystalline materials. I am taking an example of band diagram because the electrons consequence of the block function, that is the electronic state in material, the periodicity, we have the electronic state arranged in different bands, so-called it is a band structure. For metals, the different bands, conduction bands and valence bands overlap. For semiconductor, the bands are separated by gap. For insulator, the gap is larger. My question is whether this same picture is valid for glassy state, because this is the consequence of periodicity of the crystal. This structure is a consequence of periodicity of the crystal. But in glass, there is no periodicity. So it is not very difficult to conjecture that this type of picture is not valid. But you can see here, can get the answer if you compare the band structure of the impurity semiconductor. For impurity semiconductor, the N-type semiconductor, there are states, impurity states just below the conduction band. And for P-type, just above the valence band. And when you make these systems disorder, you can see what happens to these bands. There are extra states. These states are continuous, you can see. These states are continuous. But here, in disorder materials, we can still describe by band structure, these states are discrete. You can see 1 point here, 1 point, 1 point, 1 point. And there was no states in the gap, in the middle of the gap. But here, you can see the number of states within the gap. And all states are localized. And these states are very crucial to describe the electronic conduction in glasses. In electronic conduction, although it has no role in ionic conduction, because ions are very large and they cannot be treated quantum mechanically, so we have to treat it classically. But in this case, for semiconducting electronic materials, we have to consider this type of band structure in describing its electronic properties. And I want to say one thing, the density of states is not same everywhere. And you can see that there is some energy level beyond which the states are extended, not just block-like, extended. But that, below that energy level, all states are localized. So this energy separates localized states to extended state. That is states described by the block function. And similarly, there are also energy level above the valence band, and it is called the mobility edge. So in glassy materials, we have the mobility gap, not the band gap, just in crystalline materials. Crystalline materials, we have band gap between two bands. But in amorphous materials, we have no band gap. We have band gaps, but that band is separate. Nature of this band is very different, because within the gap, we have states. But in crystalline materials, there are no states. But here, we can describe by the mobility gap, between the gap between two edges. And with these concepts of band structure, I will try to explain you some of the electronic properties of glasses. It has been already been described. So I will tell you briefly how the glasses are formed, because that is essential, because if you cannot have knowledge about the glassy structure, we cannot understand its motion, the ionic motion or electronic motion through it. Although many people have talked about this, I like to give you a recapitulation. For example, silicon oxide glass. This glass is formed by a network consisting of a polyhedra, SiO4. SiO4 polyhedra means in a polyhedron, silicon is at the center, and the 4 corners are shared by 4 oxygen. And in the silicon oxide glass, these polyhedra, either sharing corner or sharing edges, form the whole 3-dimensional structure. This is for the silica glass. So the silica is a good glass former or network former, because I shall use this term again and again. So you should have clear idea about the network former. Similarly, for phosphate glass, here also PO4. P, there is phosphorus, is surrounded by 4 oxygens at the tetrahedral corners of the tetrahedral, and phosphorus is at the center of the tetrahedral. And fluoride glasses, this distribution is very complicated. And this type of structure is generally described by a continuous random network, because all structures, the silicon oxide bonds and forming either sharing corner or sharing edges, they span the whole network. Now, if we introduce in this structure, the continuous random network, some of alkali ions, then what will happen? These alkali ions, presence of the alkali, due to the presence of the alkali ions, this glass becomes conducting. Here the glasses were insulator, almost insulator. But here the glass becomes conducting. Here, if you introduce lithium, then it becomes lithium ion conducting. If you introduce silver, it becomes silver ion conducting. Then why? But this structure can be described by a modified continuous random network. That is, the network which I have told is modified by lithium ions or alkali ions. If you introduce, they are called ion conducting glasses. And if in these systems, if we add the corresponding salts, halides, for example, for lithium silicate glass, we add lithium iodide, then the conductivity of these materials, of these glasses, become very high. And that is why it is called superionic glasses. And their structure cannot be determined by the modified continuous random structure. And that's why I have a question, whatever the structure. And main question is why these glass should have very much higher conductivity than these corresponding glasses without any halides. This is the burning questions in our glass science. We have tried to solve these the questions in this lecture in due course. And if you in the glass structure introduce transition metal ions here, you can see, then surprisingly this becomes electronically conducting, not ionically conducting. Why? The transition metal ions exist in different valency states, and these ions are very difficult to move. And because of this different valence state of the transition metal ions, the electron can have localized electrons, of course, from one state to other states. And because of that, the glass becomes semiconducting. Now, before proceeding further, I want to give you a glimpse of the measurement technique, experimental measurement. How can we measure the electrical conductivity or some that it may be DC or maybe AC. For electronic conductivity, we can apply DC field and pass current or DC voltage and measure current, so we can get resistance. For electronic conductivity, there is no problem, because in every electrical measurements, we have to make a structure. We have to apply electrode. Otherwise, there will be no problem of contact. But for AC measurements, we also use the same structure, but the materials are sandwiched between two electrodes, and we apply an AC electric field. And this AC electric field I have shown here, that gives us the capacitance as well as conductance of these materials. I am not going to how these equipments works in details, but in every equipment, we measure this quantity, capacitance and conductance. Then we have, actually we can measure the impedance. That is an imaginary complex quantity using the equivalent circuits. For a simple circuit, this is the capacitance and this is the resistance or conductance in parallel. If the circuit is parallel, then we can express the complex impedance is like this. Sorry, there is a mistake. There will be I here. And the real part and imaginary part can be separated like this. You can see that one extra term, C0, C minus C0. C is the capacitance, G is the conductance, and the C0 is the capacitance of the cell. Because if there is no such materials in the cell, then there will be some residual capacitance. And by this, we can plot the real part and imaginary part, we get a circle. And sometimes, experimentally, it is an ideal curve. Experimentally, it is very difficult to get, it is called Nyquist diagram, to get a like semicircle. So circles are depressed, or circles have long tails. There is some other in the pikes that may be due to some effect of the electrodes and material interface. If we can finally calculate this from the, this is the low frequency data, and this is the high frequency data, we can extrapolate it, and then from the extrapolation we can calculate the resistance, and from the resistance we can calculate the DC conductivity, and from the conductance we can have the AC conductivity measurements as a function of frequency. For other parameters also, someone asking me how can I determine the dielectric functions. Here you can see the real part of the dielectric permittivity. We can have the imaginary part of the dielectric permittivity. You can see we have all measure the quantity capacitance and conductance and nothing else. So from capacitance and conductance, we can measure everything. Some authors also like to prefer represent it in a different way, that is modulus, which is a reciprocal of the complex dielectric permittivity, and this is like in this way. So if you have the measure capacitance and conductance, you can calculate this one, and finally the modulus real part and imaginary part. So these are these quantities that are dealt with mainly by the scientist to get information about the charge carrier movement and relaxation. Here I have shown this type of measurement, that is sandwiched between two, is possible only for a limited frequency range, 100 megahertz. Beyond 100 megahertz, this type of structure is impossible because the resistance of the contact between the materials and the electrode becomes comparable to the resistance of the materials. So we need to measure it without contact, without the help of any contact electrode. Here we use transmission line measurement. You can have the so-called gold electrodes. These samples are here, and some microwave are entering or falling on the sample surface, and they are get reflected. So by analyzing the phase and angle amplitude of these reflected waves, we can determine the capacitance and conductance, or finally you can see the impedance, and from this impedance we can get the real part and imaginary part of the conductivity. And it is very tricky problem. So up to that we can have a frequency range of up to gigahertz. This is the experimental setup which we are using in Kolkata in our laboratory. Now I will tell you about something electronic conduction in materials. Before I go into the details of this, you can see here is picture the plot of the conductivity, DC conductivity as a function of temperature. There is Arrhenius plot. You can see this is for a vanadium oxide modified by the cadmium oxide. You can see the slope is changing gradually, but at the high temperatures the slope is almost constant, but as the temperature is lowered, because 1 by T, so this side is temperature is low. You can see that is the activation. If you define activation energy in the particular range or in a specific temperature range, then you can say that activation energy is changing gradually. And for some materials, the activation energy becomes constant, but not in this case. Therefore, this type of behavior of semiconducting materials is generally explained with the help of models that is based on electronic structure, that is defect structure. I have shown the band structure of the glassy materials, and for this work, Professor Mott was the first to study this type of work theoretically, and he have shown that in this region, the conduction of electron takes place with the help of phonon. The hopping of electrons is possible only if there are phonons. So this type of conduction is called phonon-assisted hopping. But as the temperature is lowered gradually, then the phonon density is decreasing. So here there is no phonons. So how this conduction will take place? So in here he also proposed one model called variable range hopping, and in this region the variable range hopping is very much associated without phonon, and it's called the tunneling. And he also proposed that it is not the electron, but this type of disorder, for this type of disorder, there are polarons. So to take a quick view of polarons, I am taking here, I am trying to make you understand in the simplest way what is a polaron. If you have a ionic crystals, and if you make an electron passing through this, you can see here, due to the interaction of the ions and the electrons, the ions positions are distorted. And because of this distortion, it's caused some energy, so electrons are confined in the distortion field, and it cannot move very fast. So it's become heavy, and these heavy electrons is called a polaron, because it is associated with this deformation field. And you can also explain is a potential landscape. You can see that the polarization of the lattice here, you can see the polarization of the lattice and the formation of polaron. At this polaron also, of course, is distributed in a specific regions, and that is called the radius of the polaron or the dimension of the polaron. We have different types of models to describe this type of results I have shown for cadmium vanadate glasses. And first it is a Mott model, then Holstein model, then it is Sackenberg model, Emin model, and we have the so-called variable range hopping model. And I have tried to explain these models in briefly. Here you can see that is the Mott model. Mott first proposed that the hopping conductivity of the transition metal oxide glasses is possible only if they are assisted by the small polaron. That is polaron. I have seen that polaron, if the polaron is small, that is, if the radius of the polaron is small, then it is called small polaron. If the radius of the polaron is larger, that is, then polaron can overlap, and it is called the large polaron. And you can see he derived an expression like this, and it is the first paper he published it in Journal of Non-crystalline Solids, for which Professor Janoth is editor-in-chief, and in the first issue, first volume in 1968, probably 1968. This was the first article published by Mott. And he also worked theoretically for disorder materials in an extensive way, and he got Nobel Prize along with Anderson for their works in disorder states. You can see here the conductivity is expressed by a simplest equation. That is, this is the frequency of the phonon that is assisting for a conduction place, and here you can see the term that is the reduced valence state, because when in transition metal oxide glass, when you melt, there are two types of valencies, V4 plus and V5 plus. You can see here. These two states, the electron can hop from one position to another positions only because of the existence of two valence states. Otherwise, electron cannot hop. And this is the ratio of the fraction of vanadium ions, reduced vanadium ions. And we have the one term which is important, that is alpha R, that is the exponential term which I have, that is localization term which I have described, the localized wave function in a disorder. And this is the activation energy. So these are the several terms, and this activation energy depends on temperature. I have shown in the picture. For in the high temperature range, what is the high temperature? If the Debye temperature, if the temperature is higher than half the Debye temperature, then it is called high temperature by definition. And if the temperature is called low, if the temperature is less than 1/4 of the Debye temperature. you can see the activation energy changes at the high temperature. The activation energy consists of two parts. There is WH and WD. This WH is called the hopping energy, with which electrons is hopping from one place to another. But due to disorder, you can see surprisingly one term, there is the disorder energy. Now what is that energy? That energy is due to the disorder of the materials, because in disorder state, the one state is different from its neighboring states. That difference in energy of the disordered state without the application of electric field is called the disorder energy. So if the temperature is very low, you can see the activation energy is described by only disorder energy. So there is no role of phonon. And this is very much surprising. And at this activation energy, at this low temperature, this cannot be described by this equation. So he developed another theory, which is called variable range hopping mechanism. You can see according to theory, you have shown here the data which I have shown earlier in only the high temperature data. And if we assume this part not varying with compositions, then we can fit this data in an Arrhenius way. And we can get, of course, the constant value of the localization length. And we have seen that localization length for this type of materials is of the order of 1 point or 5 or 6 angstrom. So the electron localization length is very short. It is either confined one atom or two atoms preferably. As I have told, if the temperature is very low, then what happens? Then we have not enough phonon to assist the electron to hop from one position to other positions. Then in that state, which I have described long time, that is here, you can see the states. If we take this atom, this state as a reference state, then you can have, this is the nearest neighbor state. But this is the beyond nearest neighbor state. But the energy difference between these states and the nearest state is higher than the energy difference between the states and that states which is away from that state, beyond nearest neighbor. So here you can, this state, the energy difference between these two states is still lower. Then under these circumstances, electron can hop from these states, which is beyond nearest neighbors or these neighbors. So this is, it is called variable range. So it can tunnel. It is not possible to hop because the potential energy here is very high, but it cannot hop, but it can tunnel from these states to these states. This is physically what is called variable range hopping. Here, he have calculated the probability of the electron to hop from one position to another theoretically, and he arrived at a expression for conductivity. We can see it is not the activated process. It does not contain any activation energy, but rather it consists, its temperature is variation T to the power 1/4 law. You can see plot as a sigma as a function of T to the power 1/4, you can get a slope. You can get two slopes, of course. Here is the high temperature region, here is the low temperature regions within this particular temperature range. So from this slope, we can calculate the localization length. Sorry, it is not sigma, it is alpha. There is a mistake. So we can calculate the localization length and the density of states at the Fermi level. And these two parameters can be compared with their values measured from other experiments. And we have seen that these values are very close to the measured value of other experiments, and the localization length is same as you have calculated in the high temperature region using the phonon-assisted hopping. And there are other models. I do not like to describe all of them. This is one of the models in which it is supposed that there are two. In Mott's model, one of the deficiencies is that it only considers the optical phonons, but it does not consider the acoustic phonons. Here, this model also considers some acoustic phonons, at low temperatures, and derived an equation like this. And you can see here this model also predicts some coupling parameter between the phonon and the electron. This is the electron-phonon coupling parameter, and then they and differentiated it as a hopping as either non-adiabatic or adiabatic. If the temperature is high, then he is shown that the hopping is adiabatic, and if the temperature is intermediate, then it is non-adiabatic. And you can see the fit to these equations. So the Snacken's model is very suitable to describe the sum of the data in some glasses without taking into the acoustic phenomena, acoustic phonons. Here is the model. This is a very complicated model. It took long time to describe the conductivity in terms of different types of energy, phonon energy, and different types of acoustic energy, optical phonon and acoustic phonons. And I just like to mention that if we can consider, if we can calculate, simulate these results and in a different way, then we have seen that this is the best model to describe the electronic motion in semiconductor for the entire range. In Mott's model, we have to consider two models. One is the phonon-assisted model at the high temperature. One is the tunneling model in the low temperature. But here, we have considered the hopping throughout the whole range. But we have taken into account all the possible combinations of phonons, either longitudinal phonons, optical, or acoustic phonons. So we have published this a long time back, of course. And then what about the AC conductivity? For the AC conductivity, we can always, you can see here, the conductivity is AC conductivity, measured AC conductivity as a function of frequency. You can see at the frequency is low, then it is almost independent of temperature, sorry, frequency. But as the frequency goes on, it shows a dispersion. If you subtract this, the total conductivity, measured total conductivity from the DC, from this the DC conductivity, if you subtract DC conductivity from the measured total conductivity and plot it again, then you can get straight lines. What does it mean? The pure AC conductivity is showing a power law, a frequency to the power n. We can describe the data as a frequency to the power a into omega to the power s. This result states. Therefore, the total conductivity is the DC conductivity plus the AC conductivity. This is the measured quantity. So when you measure the conductivity in a spectrometer, we are measuring the total conductivity. But we have to separate it to DC as well as the AC conductivity. And the AC conductivity here can be described by the polarization function as a distribution function, because in potential wells, in disordered glass, in glassy materials which are disordered, there is a random distribution. And if we assume this distribution, and you can assume that this is the tau is the relaxation time, then we can calculate the AC conductivity theoretically and compare it with the experimental data, and we can get information about relaxation time and other quantities. So we have to consider different models. For this also, we have electron tunneling model, we have small polaron tunneling model, large polaron tunneling model, hopping model, and so on. And we do not know which of these models are true for these materials. So we have to compute all these models, parameters. Here we have the tunneling models. In the tunneling models, relaxation time is assumed to be like that. This is the atomic tunneling model or electron tunneling model. And finally, we get the conductivity in this form and the exponent, which is very crucial. It is independent of temperature in this model. I am telling you the consequence of the conductivity and the frequency exponent, because we will get information on the particular materials with this help of this theory. And for this small polaron tunneling, the relaxation time is assumed like this, and consequence of which is that the frequency exponent can be expressed in this way. So in this small polaron tunneling model, you can see the frequency exponent is dependent on temperature, and as the temperature is lowered, the frequency exponent gradually decreases from 1 to some fixed value, or 1 to some, there is no limit of decreasing. For other models, there is a large polaron, then we can see the frequency exponent is related in a complicated way, and here is the conductivity, and we can have shown here the result of our analysis using this model, and you can see this is the exponent and this is the conductivity as a function of temperature. We have fitted this conductivity and the frequency exponent simultaneously with the different values of the parameters. These parameters are, there is a localization length, and other parameter is the polaron radius. We calculated these two parameters from this fitting, and we can see that there is a perfect agreement between theory and experiment for conductivity as well as the frequency exponent. So this model is one of the best model to describe the electronic conductivity, AC electronic conductivity in semiconducting glasses. And another model is that the correlated barrier hopping model. Barrier hopping model, when the except without tunneling, the electron can hop, I have told earlier. This model predicts the conductivity in this form and the exponent in this one. Here also conductivity exponent decreases with temperature, but you can see that is a fit. It can fit a limited temperature region. Beyond that temperature, this model is not valid. So hopping is valid only at high temperatures, but the large polaron tunneling is valid for the entire temperature range. So I have described the DC conductivity as well as AC conductivity considering the polaron models. We have shown that in conclusion that the Emin's model, which is the most general, which considers the phonons, acoustic phonons as well as the optical phonons, is the best model to describe the DC conductivity, and the large polaron tunneling model is the best model to describe the AC conductivity. So guys, you can imagine that the conduction is taking place of electrons either under DC field or under AC field, but the two models to describe these two AC and DC are separate. What does it mean? That means that we have assumed earlier that the total measured conductivity is the sum of the DC as well as the AC conductivity. So this assumption, although it was a very tacit assumption, but experimentally we have shown that this assumption is very correct. Now I will describe you the most vital part of my talk, that is called the AC conduction in materials. Conduction of the ionic conductions. To describe ionic conduction, I have already shown you this picture, the silicon oxide. And when the silicon oxide is modified with some alkali ions, you can see the picture here, that the alkali ions are in the gap, in the void space. And you can see also there are there is a gap between these. You can understand that chemically, when you add sodium ion, for example here, sodium ions or lithium ions, we can break one bond and we can form a bond like this. So this oxygen have an extra electron, and that electron, that bond is satisfied, neutralized with the addition of sodium ions. So the alkali ions is forming a so-called ionic bond that is a loosely bound, and there are non-bridging oxygens. So by introducing alkali ions in silicate network, we have non-bridging oxygen. You can see the oxygen ions ending, forming no other bonds on other sides. But here oxygens are forming bonds on two sides. So there are non-bridging ions and alkali ions. Non-bridging oxygen ions and alkali ions. These are the structural models which we consider for conduction hopping. This is the molecular simulated results. When we apply electric field to these ions, one of the ions, then there is other ions, vacant positions, ion can move when because application of the electric field reduce the barrier between these two sides. And due to reduction, the ion from here can hop to other vacant positions, which are described by this diffusion equation. And if this diffusion equation is described by this, then we can get the mobility of these ions using the non-Einstein relation here, the diffusivity here, and then we find the conductivity, sigma is equal to Q n mu. Then my question is, we can measure experimentally this parameter, but we cannot measure that this is the charge carrier concentration and the mobility separately. So this is the main problem which are giving us for studying the ionic conductivity. If you can measure separately, but for electronic materials, this was not the case, because by Hall measurement, we can calculate the charge carrier density for electronic charge carriers. And mobility we can measure otherwise. We have time of flight experiments, that is, we can inject an extra electron in materials, and we can observe the time of flight when it is decayed. So by measuring the length and time, we can calculate the mobility. So these are for quantum particles, like electrons and holes. But for sodium ions, which are classical particles, this is not valid. This is not possible to get some people have tried to measure the charge carrier concentration using Hall effect, but different people have got different results for the same glass composition. So it is under doubt whether these materials are, these measurements are true. So our main problem is to separate the conductivity and the mobility from the measured conductivity. Since we cannot do it, we have tried to adapt some technique to simulate it using a particular theory, what is called linear response theory. Now, we can also describe these motion of ions in a glass structure separately. Practically, you can see there are bridging oxygens, that is oxygen that was not that was taking part in bonding, and there are oxygen that was not taking part in non-bridging oxygens. Non-bonding, it is a forming ionic bonds. So when an ion moves from one place to another place, we require two energy. One is this is the binding energy, because you have to separate it from its bonding from these non-bridging oxygens. And other energy is that it is to move through to bridging oxygens. So if the length is shorter than the diameter of this, it cannot move. So it has to dilate this structure so that it can move. So it requires some strain energy. So total activation energy for hopping from this side to this side, if you have a barrier, then it consists of two parts. One is the binding energy, other is the strain energy. And theoretically, it is Anderson and Stuart long-time model calculated in this way. And we have also calculated for various materials. And it's shown here, the potential energy landscape before the ion is there, and this landscape, change in landscape when the ion is hopping from here, hop from this side to that side. This is the change in potential energy landscape. And I have already expressed the conductivity in terms of charge carrier concentration, and the charge, it is the mobility, because the charge is different for different alkali ions. And if we assume that this is Arrhenius, charge carriers Arrhenius with some activation energy, so-called creation energy, and the mobility also with the same type of behavior, it is called the migration energy, then ultimately we can express the conductivity this as a function of this, which is sigma 0 by T and some exponential by activation energy by kT. And this is the theoretical value. So if we plot sigma dCt logarithmically as a function of 1 by T, we get a straight line, so we can get the activation energy from this straight line. But most people are accustomed to plotting sigma dC as a function of 1 by T, and that was the Arrhenius relation, because that was first the empirical plot, but this has some theoretical meaning I have shown here. So there are some models to describe the ionic conduction in this. Mainly, I have classified these. There are many models I have listed here. but there are only two models which are very essential, very much important to give us a picture of the, one of the is the weak electrolyte model proposed by Socket, with whom Anna did his PhD, yeah. He proposed one model, the weak electrolyte model. He assumed that the ions, the oxides that is are in the dissociated, and all ions are taking part in the conduction process. So it is the mobility is not changing here, but the concentration is changing with temperature. And in the strong electrolyte model, here the concentration is not changing, but mobility is changing, because we assume that all ions are taking part in the conduction process. So there is no change in the concentration of the ions as a function of temperature, because there are no more ions to take part in this process. And these are some of the models. I don't like to describe in detail, and you can see that the cluster models, and the weak electrolyte model, the diffusion path model, all of these models assume something about the number of mobile ions and the mobility. Here we have shown one of the two-dimensional picture of a model. Here you can see, which is very much applicable to silicate glass. The glasses are here, there are some conduction channel, and in the conduction channel, the ions are moving. And the rest of the glass structure, the ion in the, is not taking part in the conduction model, and so this is very similar to the weak electrolyte, because all ions are not taking part in the conduction process. Here is the most general things in a wide spectrum. If you consider a wide spectrum, then what would be the different types of polarization we met? You have this picture in textbooks. In the long time region, the time is very short here, and here is the time is very long. That is, in otherwise it is frequency is very low here, and in this region frequency is very high. If you go from high frequency to low frequency, we can get the different types of polarization: electronic polarization, atomic polarization, orientational polarization. The atoms are the dipoles can change its orientation, and hopping polarization. We are in this region, the one position to another, an ion can hop from one position to another positions, and there is a space charge polarization. This is our enemy. The space charge polarization is our enemy, because for every experimentalist, when you make an electrode, then there is a space charge polarization. And this poses before us an difficulty, how to get true information from the measured quantity. Even for glassy materials, it is we can eliminate it in a different way, but for polymeric materials, this interfacial effect is very strong. Here I have shown the conductivity spectra. You can see there in a wide frequency range from 10 hertz to about 3 gigahertz. You can see here there is a change in the slope after a particular frequency, and this change in slope is not so high, but after a particular frequency the change in slope is very high. Drastic change in slope. Here there is no slope, you can see here. Then slope starts, dispersion starts, and the dispersion is small, and as the frequency is very high, the dispersion is very high. So these two regions can be separated and can be described by these two empirical laws. One is the Jones-Star law, modified by Almond and West in the low frequency region, in this dispersive region. Here it is called the DC conductivity as a function of the omega by omega to the power. This frequency is the crossover frequency, where DC to dispersive frequency crossover starts here. And the exponent is always less than 1. In the high frequency regime, here we can see it can be described by another power law, and that power law, the exponent is greater than 1. So we can at least assume that the mechanism of conduction or AC relaxation, whatever you call it, is different in these two regions. So I shall like to focus primarily in this region, the low frequency region, which can be characterized by these equations, so-called modified Jones-Charles law. So we have at our hand, but is there any theory which can at least describe qualitatively, although not quantitatively? And to get this information from this relation, I am showing you two contrasting facts about the ion dynamics in glasses. Here you can see the metaphosphate glass, silver metaphosphate glass, in which we have silver iodide doping. You can see the drastic change in conductivity from no doping to a fraction of 0.6 mole percent. There is a change in conductivity by 5 orders of magnitude, and this is what is called first ion conduction. And here I have shown a different effect, opposite effect. If you do not change the glass former, but if you replace one kind of alkali by another kind, and if you plot, you can see that the conductivity changes reduced drastically. Here the conductivity increases, here the conductivity decreases drastically by of the order of 5 orders of magnitude, and it is called the mixed alkali effect, or sometimes we got mixed mobile effect, because for this it is not necessary to participate 2 kinds of charge carriers. If you have more than 2 carriers of charge carriers, then we can still observe this type of effect. So this is generally called mixed mobile ion effect. And my question is how to explain these two phenomena. You can see there is a minute change in the fraction of silver iodide, whereas there is a large change in conductivity. Here also there is 2 types of mobile ions, but total content is same, but there is drastic reduction in conductivity. So we have tried to explain these phenomena using the help of linear response theory. I have already described this. The main consensus in describing this to the ion dynamics, because I have already told that separation of mobile ion concentration and the mobility is very difficult from the experimental conductivity. And another thing which I have not told is our incomplete knowledge of the microscopic local structure and the local environment of the mobile ions. When the mobile ions is moving, then its environment is also changing, because the bond length is changing, bond angle is changing. So if we cannot determine these parameters experimentally, we cannot exactly determine the mechanism of conduction, what is happening when the ion is moving. And this is a glimpse of linear response theory. When there is a charge carrier, because you see number of charge carriers in a pool of charge carriers, there is some fluctuations. If there is a fluctuation, if you pull the electric field or the cause of the fluctuations, then there will be dissipation. Here, the electric field is the cause, and if we remove the dissipation function, then we can have a correlation with the current at time 0 and the current density at a particular time. Then we have a correlation function. Then this correlation function can give us the complex conductivity according to this theory. And this complex conductivity can be separated into the real part, and we can see finally that the real part of the conductivity consists of several parameters that is called the charge carrier density, and here one thing which is called the Haven ratio. This HR is a Haven ratio, considers the correlation between successive hop, because ions are not independent. One ion, when one ion is moving, other ions are also interacting with it. So there should be a correlation between 2 successive hops. And that correlation successive hop is called the Haven ratio. And you can see from this expression, when time is short, and this quantity is the square of the displacement of the mobile ions. That is, when ion is moving, it is covering some distance. Since the movement is random, so we have to the average value, and its square is meaningful. you can see when this displacement is small, then we can see here the time is increasing from this way, whereas frequency is increasing this way, because these are opposite. When time is short, you can see that the displacement can be expressed as a function of time as a power law, you can see. And the ion is characterized by the non-random backward and forward hops, and as a consequence of which that the conductivity is omega to the power n, that is just like this in this region. But when the time is long, then there is a crossover, you can see. Time is long is crossover from that is dependence as t to the power 1 minus n to linear time dependence. In this region, you can see after crossover, the ions can execute it here an unrestricted motion of random step, and finally the conductivity becomes independent of frequency here, you can see, and expressed by this relation. So there is a jump in the from DC to the dispersive region according to the Rayleigh response theory, at least qualitatively, but there is a jump is sharp. But experimentally we have observed that the change is very gradual, and the very gradual dispersion gives us some idea about the relaxation mechanisms. So after using this theory and our experimental spectra, we have calculated DC conductivity and the crossover frequency. We can see that DC conductivity is Arrhenius, the hopping frequency is also Arrhenius, and with the same activation energy. What does it mean? If we consider this, we have measured experimentally with some activation energy, and if we measure the hopping frequency with some activation energy, with the same activation energy sigma and omega h, then what about NC? This C is the constant. So if the activation energy is same, then the charge carrier concentration has no activation energy, that it is independent of temperature. Let us see the result. Independent result, that is activation energy is slightly dependent on temperature and also slightly dependent on glass composition. This is surprising. The glass, the charge carrier concentration is not strongly dependent on the charge carrier concentration. Here we have plotted the charge carrier concentration as a function of the silver iodide content, the halide salt. You can see that independent of temperature. We have taken two value, Haven ratio 1, that is, if the Haven ratio is 1, there is no correlation between charge carriers, there is uncorrelated motion. And if there is some correlation, I have taken the value of 0.2, there is strong correlation. But you can see that the charge carrier concentration does not change drastically, just by a fraction. And here we have seen the total charge carrier, the charge carrier coming from silver iodide and silver oxide. And here is the charge carrier coming from only silver iodide. In some of the electrolyte model assumes that the charge carrier is coming from this. So according to our calculation, we have seen that neither of the strong electrolyte model, not weak electrolyte model is satisfied for these glass systems. So because all these theories basically depends on some assumptions, strong electrolyte models as well as weak electrolyte models. But here the linear response theory is most general. So if we simulate our results with this theory, then we can get some results for this particular glass structure. Neither is obeying solid electrolyte, strong electrolyte models, or not weak electrolyte model. Here we have shown you the frequency exponent. Here you can see the frequency exponent is almost independent of temperature and near about 2/3 for these glass systems. And so far, we have also plotted for several other glass systems also. There is little deviation from one system to another systems. And what does the exponent tell us? One guy predicted some value for the exponent. You can see he have shown that if the value of the exponent is 2/3, 0.66, then it is the conduction is 3 dimension. And if it is 2/5, it is 2 dimensional, as 1 by 3 it is 1 dimension. So our value of 2 by 3 corresponds to 3 dimensional motion in this so-called the super ionic glasses. But we have also shown that for mixed alkali glasses, this type of motion, the dimensionality of this conduction space is 2 by 3 as a 2 by 5, and it is less than 2 by 3, as a consequence of which the conductivity is 2 dimensional, and that is why when we mix 2 alkali, its conductivity is decreasing, because the dimensionality of the conduction space is decreasing. So this theory equally explains the mixed alkali effect also. Now I have tried to calculate some parameter from this linear response theory and correlate it to the so-called the conductivity, whether the conductivity or ion transport here depends on some structure. Because to show some structural connectivity, I have calculated these 2 parameters. One is the parameter, there is a length scale. The length of the mobile ion, the displacement of the mobile ion at the crossover point. So we can calculate it by taking the just a Fourier transform from the conductivity spectra, and we can show here another parameter, that is the long time behavior of this displacement, when the time is very low, sorry, very high. So you can see here the Fourier transform of the conductivity and the displacement of the material of the ions as a function of time. You can see that there is a crossover from one type of, this is in the subdiffusive region, and this is the diffusive region. Here is a proportional to t, here is here is a proportional to t, here is proportional to t to the power 1 minus n. So there is a crossover from this region, and if we calculate this crossover length here from this, the r square at Tp, that is the transition point is called Tp, and if we plot this, then you can see that it is behaving like a similar way as the conductivity. Here we can see the conductivity was decreasing, increasing with the increase of the so-called the lithium ion content. And also the long time behavior is also behaving like this same thing. So we can at least correlate the conductivity and the length, particularly characteristic length in such glasses, because the glasses and the ion dynamics in these glasses are not a fixed parameter, it is dependent on the structure of the glasses. And we have also, now I shall tell you something about mixed alkali glasses, mixed network former glasses, because when the glass former are changing, but the charge carrier concentration is kept fixed, still there are increase in conductivity or decrease in conductivity, and these are called mixed network former effect. Here we can see that is the silver borophosphate glass, the boron oxide and phosphorus oxide. We are replacing phosphorus oxide by the boron oxide, and also we are changing also the silver ion content. When the silver ion content is 0.5, you can see there is a 1 peak, 1 maxima. But when there are lower silver ion content, we see 2 maxima. Similarly, we can see the minima, 1 minima and 2 minima in the activation energy. So, and this is what is called the positive mixed former effect. That is the occurrence of the maxima in the conductivity as a function of the glass former ratio. If it is positive, higher, then it is called positive glass former effect. Even we can have negative glass former effect. I will show you. And how can we explain this? We explain this in the same thing, in the similar way. We have calculated the mean square displacement or mean displacement here. We have shown that the crossover. So we calculate the value of this at the crossover time, and we have plotted it as a function of compositions, x, 0.5 compositions. You can see there is a peak in the same compositions as we have observed in the conductivity. So at least we can predict that the ion dynamics is not static. It is a dynamic parameter. So it depends on some dynamic parameters, that is crossover length, or so-called the length of at the crossover time or crossover point. Here I have shown the long time behavior of this parameter as this is at time t is equal to infinity. Particularly this corresponds to DC conductivity. You can see the opposite behavior. For 0.5 there is a 1 minima, and for 0.4 there are 2 minima. And this corresponds to the similar behavior to the activation energy. Or if you calculate the average silver-silver distance here, you can see that silver-silver distance, the behavior of silver-silver distance is same like that. So we can at least predict that this parameter is very close to the average mobile ion distance in the glass system. Then what we have tried? We have tried to calculate the density of the glass forming unit here. Here is the BO4, BO3. I have told in the very beginning that all glass consists of glass former unit. For example, silicon SiO4 unit, but here the system are two. Here is PO4 unit, here is BO4 and BO3, trigonal boron oxide network, and so tetragonal network represent. In the first talk of the first day, Professor Eckert also shown some results with silver ion or sodium ion, sorry, not silver ion, lithium ion conductivity, and he correlated this connectivity between these networks using NMR. But we have tried to understand this using the Fourier transform infrared spectra. Here we have the borophosphate glass. We have tried to deconvolute this spectra to calculate this BO4 or BO3 units, and also PO4 units. It is in the other frequency range. But then we have calculated the population density of these. We can see we have plotted here the relative area of BO4 unit, and as a function of compositions, we can see that the same maxima at the same compositions. So the structural units which are very important to describe this type of materials, and that is the ionic conduction in glasses, is also important. We have also compared our results with the NMR measurements. Here one group measured the same thing using NMR, but their composition range is limited, but they have observed the same maxima in the same composition range, at the same compositions we have observed. So our results is also very similar to the NMR results. So we can get the same information from infrared spectra as you can get from the NMR spectra. In terms of NMR, they are the connectivity between phosphorus, boron, or lithium, boron. Same thing we can get it from this infrared spectra. Here I have shown some interesting results for some unconventional glass. Here you can see that boron oxide here, we have replaced it by some heavy metal glass format. Bismuth oxide is a heavy metal glass format. You can see that several minima, but in all cases the conductivity decreases. So it is called the negative glass format effect for bismuth glass. And we have correlated also it with the length scale, the tau at the crossover point, and the long time behavior of the length scale. We can see these two parameters, or these three parameters in this case, behave similarly: the DC conductivity and the crossover point and the long time behavior. So this result is very surprising. These are our recent results published thus in the December issue of Journal of Chemical Physics. And here similarly we have also deconvoluted the spectra and obtained here the BO4. Because in this BO4, BO3, and we have also BiO6 units here. BiO6, we have calculated everything, but they are not related to this the dynamic process. Only the dynamic process is controlled by the BO4 unit. You can see the opposite link here, the opposite, no, sorry, the similar behavior with that of the conductivity. So we can at least predict that the dynamic process is related to structure, either to its length scale or to its network former unit. So it is not a static. You cannot describe in a static way. And this is the main conclusion, what I have done here. Now I shall describe, in absence of the scaling model for the conductivity we have developed, because the scaling is important feature in data analysis. The ability to scale the conductivity isotherms at different temperatures in a conductivity range, temperature range, or in a frequency range in some particular superposing a curve, common curve, that indicates that the process can be separated into a common physical mechanism, and that is modified by the temperature scale. And we have, in our calculations, we have shown that we have obtained one results from the consideration of the dielectric spectra, that the DC conductivity can be related to the hopping frequency. You can see here with the Haven ratio, because Haven ratio is very important in these types of glasses. And when we plot the DC conductivity, scale the AC conductivity, as you have shown, by the DC conductivity, and the frequency axis by the crossover frequency, we get the function as a frequency plot. Then we can have one common curve, which is independent temperature as well as independent of compositions if there is no structural change in a specific composition domain. And this model is very simple, and people are using this and referring it as Ghosh scaling model. I can have several publications here by different authors who have referred to it as Ghosh scaling model. And they are using, even this year I have seen up to that 15 papers in which they have analyzed this data using this model, and they have referred it as a Ghosh scaling model. The essence of the model is that if you plot the conductivity, you can see here the scale, the conductivity in the fashion I have told, then we have two curves here, because we tried to, for telluride glasses here, we have detected this, because the glass structure of the telluride glass structure was published in Science, because at a particular compositions of the alkali halides, when we increase alkali, not halide, but alkali oxides in a silver, in a tellurium glass matrix, then we can observe that the tellurium systems, there is a structural change from TeO4 unit structural unit to TeO3 structural unit, and intermediate between there is even 3 plus 1. There is 4 coordinated structural unit to 3 coordinated structural unit. When the structural unit are 4 coordinated, this structure is rigid. When the structural unit is 3 coordinated, so planar structure, the structure is floppy, they have told. And there is a transition. So my question was whether we can monitor this, we can observe this with the scaling parameter. So for a composition range, there is a scaling, and for another composition range, there is another scaling. There is 2 scaling are superposing, not superposing, they are separated according to our mechanisms, model. Here I have shown one results from, they have studied the phase transition of this material, polycrystalline materials, VI phase transitions, and before transition, they have one type of superpositions, and after transitions, they have what? Because the transition depends on temperature. Even they have tried to understand, they have just, some authors are plotting this in this way, and they are predicting that there is a transition at this point in the reverse way. There is also another, they have also plotted like this in crystalline materials, mixed crystal. They have tried to understand the conductivity spectra using our model and dynamics. I have shown here the mixed format effect glasses here. You can see that is the perfect composition for temperature as well as for composition. I am changing is the silver ion, molybdenum oxide and phosphorus oxide, and you can see as a function of temperature it is perfect superpositions. As a function of composition it is also perfect superpositions. But here for silver borophosphorus glass, for which I have shown the results, you can see the superposition is not possible, because in these systems, throughout the all glass forming region, there are one type of structural unit. And for these systems, there are two types of structural unit which are dominating in the conductivity. Because population density of PO4 in a particular composition range is different from that in the other composition range, which I can, here you can see. If the composition range is like this, 0 to 0.5, then there is perfect superpositions. So in this composition domain, there is one type of mechanism. Here also in the 0.6 to 0.1, for the same composition, for the same glass systems, but with different composition range, you can see the perfect superpositions. So this is according to our models, which predicts that if there is no structural change in a particular composition range, then there will be perfect scaling. And if this structure changes, there will be change in the scaling parameters. Now, I have also developed recently one scaling model, which is dependent on the microscopic scaling model, so the length scale of the ion displacement. And the model is very simple, you can see. I have scaled here the displacement as the displacement at the crossover time, and the time axis by the displacement at the crossover time. You can see a perfect superpositions for a number of glass. This is silver phosphate glass, the one data, and the silver phosphate glass is modified by silver iodide, and the silver phosphate glass are modified by cadmium iodide, because in cadmium iodide glasses, this very interesting glass, they are not mobile, but they are making some of the silver ions mobile. But here we can see that there is a perfect superpositions for the mean square distribution. That is, what does it mean? Also, this scaling is also consistent with our previous scaling, that is scaling of the conductivity, macroscopic scaling. So microscopic scaling is very much similar, is supported by the macroscopic scaling. And then what does it mean? Why there is some the microscopic length scale for different compositions should be the same, because in this composition range, the mechanism of ion dynamics is same. The change is not changing, and that is the conclusion. Lastly, I would like to show you the relaxation of the charge carriers in glassy materials. I have considered this glass system, that is selenium system. It is a glass former, and it is a modifier, and it is a salt. I have shown here, it is a representative, and this dielectric spectrum here you can see that is, it's at the function of frequency. At the high frequency region it is almost constant, but in the high frequency, as the frequency is low, you can see there is a drastic change and in this region. And this is I have told, due to electrode polarization effect, because dielectric constant cannot change from of the order of here to 20 to of the order of 10 to the power 3. So that is why I was telling that this is our main enemy in the measurement. Here also we have shown here the dielectric, the loss parameters. It shows some dielectric loss peak. So to describe these parameters, the dielectric relaxation in glasses, there are several functions that have been described. I can see the Debye relaxation process. Here, there is no distribution of relaxation time. But there is cold distribution. Here, there is distribution of relaxation time, as well the the so-called relaxation parameter alpha and delta epsilon. There are also Cole-Davidson model. Here also it is considered the distribution of relaxation time differently, and we have mostly used, particularly in glasses nowadays, but earlier it was mostly used in polymer, that is the Havrilak-Nigami H-N function, and that is divided by, given by this type of parameters. So these are the functions which are mostly used in describe the, but experimentally, when you measure this, when you try to fit this, we have to consider the electrode polarization effect. So we have to add some additional function. We have to model it. We have to add some additional function that can describe the electrode polarization, and you can extract the true results from this. Otherwise, our estimation of the relaxation mechanism will be very wrong. We can see here the modulus representation. I have seen many authors have preferred to represent data in this way. That is the real part, and this is the imaginary part. In a modulus representation, here the electrode polarization effect is suppressed. So this formalism has some effect, but is applicable, is very easy to analyze here. This the peak in every materials occurs because of the nature of the imaginary part of the modulus by definition. And main way our purpose is to calculate the relaxation function, which relaxation function can define the relaxation parameter in the most elegant way. So here you can we can express this as a the function as an integral of some decay function, and then decay function we can also use it as a either is a Havrilak-Nigami function, or it can be taken as a so-called the Kohlraasch-William-Watt function, as Professor Eckert told in the first day. But whatever may be the reason, whatever may be the nature of functions, but our intention is to calculate the relaxation function elegantly. Here I have shown the relaxation function of these materials in the three-dimensional, this temperature dependence and the time dependence, as well as this is the function. You can see that it is very difficult to calculate it in a, it is not difficult, in a difficult also, of course, but here what you have like to say that, to state that the exponent here in the Cole-Raasch function, the exponent beta can give us an idea about the nature of distribution of relaxation times. Here the beta is always less than 1. For our system, I have, so in the selenide system, it is of the order of 0.5 or 0.4, depending on compositions, and so that it indicates the relaxation is strongly non-exponential. Therefore, in glasses, in every glass, the relaxation is strongly non-exponential because of the strong distribution of relaxation time, and that arises from the distribution of potential landscape in the glassy materials because of disordered nature. So I would like to acknowledge my workers, co-workers, my students, and the funding agencies, and thank you all.
I just want to know that for ionic conducting glass, the low phonon glasses are suitable for ionic conducting glass. The selection of the glass composition. So it is suitable to select some low phonon glasses?
Maybe, because there is no such restrictions. That is, the glasses should be low phonon or high phonon glass. If the melting, the low phonon glass is something lower, I think so.
Yeah.
Melting point.
Yeah.
So it cannot operate in a, because we should be always below glass transition.
Yes.
Below glass transition. If the low melting, low phonon glass have some considerable range of glass transition temperature, then it's okay. It is not a possible, it is impossible to study the ion dynamics in
because the phonon has a role in the conductivity of the glass.
But
another, I also have done one work with this bismuth containing glass conductivity. There also it is decreasing. I have also found in lithium disilicate glass.
Lithium disilicate glass.
Yes.
Silicate glass,
Yes,
not
silicate.
bismuth. But
No,
containing
but
bismuth?
I add bismuth like you have done in your lithium borate glass.
Yeah, yeah.
There also I found decreasing trend.
Because there might be mixed network Forman effect. Because you have silicon oxide
Yes.
and also bismuth oxide. Bismuth oxides can act as network former.
Yeah,
I have shown.
but I think network former is in a high concentration. Bismuth, if network acts as a network former at high concentration.
So because in for
low concentration
system
is
always decreasing.
So here bismuth has also two types of ionic states. Maybe in +3 or it may be in +2 or plus. So here it can be also ionic conductive.
Electronic conducting.
Electronic conductivity. So there is two roles. One is ionic due to lithium ion and electronic due to the bismuth.
Yeah.
So is it affecting the whole conductivity of the glass?
Yeah, right. Yeah, good question. But you should remember the magnitude of the conductivity. Whether the electronic conductivity is very high or the ionic conductivity is very high. Which one is comparable? In such glasses, I have measured the XPS. I have not shown here. And calculate the density of bismuth 6+ and 5+. Okay? But I have shown it there mostly in 6+ test. So if there is a slight existence of bismuth 5+, so if the electron can be hopping, then it's very small conductivity we have compared to the ionic conductivity. So in this system, our system, there is no role of electronic conductivity. We have checked, but you have to check by XPS whether if the content of bismuth is high, particularly.
If we are adding bismuth in the glass, so we are modifying the glass because bismuth concentration is very small, around 5 mol% or like this. So it opens the structure of the glass. So in principle, the conductivity should increase. Because
no, it may not. It can take part as a network former. In my case, it is network former, not modifier.
Bismuth may be in high concentration.
Yeah.
In my case, it is low concentration.
Low concentration.
So it is may not be a network forming.
It will be network former.
Oh. Okay.
So just I want to know, suppose you are telling something about silicate glasses. So what about the conductivity of suppose chalcogenide glasses or new glasses, fluoride glasses?
Yeah.
Any idea?
Yeah. The conductivity of chalcogenide glasses,
We can dope with iodides, some iodides.
Yeah. It may be higher or it may be lower. Normally, the chalcogen glass have some lower conductivity. It's comparable to the electronic conductivity in semiconducting, the transition metal ion glass. Okay? But the fluoride glasses, as you are telling, have lower conductivity. I have worked extensively with fluoride conductivity, fluoride glasses, but I have seen that the conductivity is very low.
What is the reason for that?
Because of the complicated structure. No, fluoride glass means zirconium fluoride glass. This is one of the glass formats, zirconium fluoride. You have a many multi-component systems because it cannot form glass by itself. You have to add some modifier, calcium fluoride, or some lithium fluoride and yttrium fluoride stabilizer. So by adding so many components in these systems, you are blocking the conduction paths. You are blocking. So many bridging bridging network is forming. So structure is not so open.
So similar, I think, for chalcogenides also. There are covalent bonds.
In chalcogen, the mechanism is different. Because there is dangling bonds, bond length. So there might be some electron hopping between one dangling bond to another dangling bond. If the concentration of the bonds are very high, you can change it by monitoring the compositions. So in some cases it is very high, but in some cases it is very low.
So there is a possibility.
Yeah, possibility. Exactly. Hello.
Professor Ghosh, I have similar questions. Like you mentioned about the lithium halide glass mixture with lithium phosphate systems. Because in your example is lithium iodide, so the iodine doesn't move very easily, right? But I just wonder, what if it is lithium fluoride? in the system without I think the flow rate is small enough and it's not a network former. So can flow rate also move, and how would that affect the overall conductivity of the glass?
Yeah. It depends on the concentration of fluorine, of course. Yeah. Because if the lithium fluoride content is less, then the fluorine content will be less. And some of the fluorine will also will be taking part with some the other ions, lithium ions also in bonding network. Not in loosely bound ionic bonds. So the conductivity of the fluorine ions may be possible or may not be possible, because we have now two ions, fluorine ions, negative, and also lithium ions, positive. So it is very important to see the mixed alkali effect here. Because fluorine, I have told that the mixed alkali effect is not necessarily confined to the alkali ions. Because I have observed this effect in fluoride glasses also, where there are three types of ions: sodium ions, lithium ions, and fluorine ions. So here, it is a strong possibility of mixed alkali effect. So conductivity will decrease first.
Yes, but if I understood well, in the case of lithium iodide, the iodide does not take part in the conduction. Okay, so it increases the conductivity because some other effect. Well, I have a question. You showed several ways of scaling.
Yeah.
Okay, including Ghosh scaling.
Yeah.
But do they show all the same thing?
No. Because the scaling parameter is different. Because in Germany, Professor Funke and his group, Rolling and Ingram from UK, they have developed one scaling model in which they only use the DC parameters to DC conductivity to scale the frequency axis as well as scale the conductivity axis. Okay? But in that way, the frequency axis is not dimensionless. It depends on temperature also. Sigma dCt, they scale this. There is frequency axis depends on temperature. Similarly, other scaling model which I have mentioned side bottom in USA, Creighton University, he used the dielectric constant as a scaling parameter. Because it is very difficult to get the dielectric, zero frequency dielectric constant is very, very difficult because of polarization experimentally. So these models are also maybe suitable for describing the ion dynamics in this in a different way, maybe suitable.
Okay.
Because in one of my papers I have shown in Journal of Chemical Physics, my student for lithium bismuthate glass applied the Funke scaling model. He observed the scaling for temperature, for different temperatures. But for different compositions, he did not observe the scaling parameters. That means it cannot predict the composition dependence of the scaling.
It cannot predict any change in structure.
Yeah.
Okay. Okay.
Okay.
I have a pet question.
Question is question.
So, most of your data and explanation is below glass transition temperature.
Yeah.
Is there an effect of the effective temperature, or cooling rate, or forming history on
the
various
dynamic process?
conductivities?
Definitely. Because when you prepare the materials with high cooling rate, for example, then the effective temperature will be different.
Right.
So below freezing point, the glass structure may be slightly different.
Yes.
So if it is different, then it will also, the dynamics of charge carriers in that particular system, that will be different. So it is strongly dependent on the effective temperature.
So how do you take into account that in your theories, in your measurements, the effect of effective temperature?
I have not taken into consideration.
Okay,
Yeah.
Okay, I see.
Yeah. But it's nice to consider.
Okay.
So we can actually, one can prepare glass with different cooling rates, and then we can study one can study the dynamics process with these two materials, and then can observe either it is strongly dependent on compositions or not dependent on compositions. But the composition will not change drastically, I think so.
No, composition will not change. No.
So this scaling will be still valid. The same type of scaling will be applied.
Okay.
Dynamic process.
So
Hi, Professor. During your presentation, you told us that we can't observe the ionic surroundings while the ionic conductivity is taking place. Why is that? Because we have techniques that can observe like the ions and its surroundings.
I cannot understand. You are telling that why iodine is not taking part in the conduction process?
No. You said during your presentation that we don't know the surroundings of the ion when it's moving during the conductivity.
Yeah.
But we have techniques that can observe surroundings of specific ions. NMR, for example. So why do you think we can't observe this?
No. When ion is moving, then in the dynamic process, that its environment is important to know, to predict its dynamical the movement. Because when ion is moving, it is surrounded by some other ions. So when it is moving, that correlation, there is the bonding between the other ions should also change. Because when it is going to another place, then there will be new bonding. So there will be structural relaxation. Okay? So in a perfect model, we have to consider all these things to get idea about the ion dynamics. Otherwise, it is not perfect. Right.
Okay, any more questions, comments? I still have a comment, but I think it's easy to talk to you personally. No, you showed in it was electronic glass, bending like this, and then suddenly a more deep change. Why was it? So why we can have something like this in electronic glass? But you show. I think it's better if I discuss with you after.
Oh, okay.
I can. No, not this one. No, not this one. No, I ask you after this. Any other comments? I would like to know, so Professor Ghosh showed some glass with mixed conduction. This tricks me, for instance, silver oxide and vanadium oxide. Right. But you treated the glass as electronic. Ionic. But you cannot apply Ionic model to silver oxide and vanadium oxide glass.
For binary vanadium oxide and silver oxide glass, we have applied the electronic conductivity model.
Yes.
Because here the vanadium content is high. And silver ion content is low.
And you think you can really neglect Ionic conductivity?
No. The Ionic conductivity is not taking place there.
It's not taking place?
Yeah. It is only the electronic conductivity. But when the vanadium content is low, the opposite case, then there is Ionic conduction. Because silver content is high.
Okay, but theoretically, at least, it will always
there will
have
be some, but the conductivity, magnitude of the electronic conductivity is so high compared to the transference number is very, very small.
No. Okay. Any other comment? Let me see. We have been discussing a lot already. We have some opposite results, as he mentioned, about the Hoping frequency and so on. So
you are my enemy?
Not really. No, not really. In the opposite. I want to be your friend. to solve this problem. We must now solve this problem.
Just one quick question, again out of curiosity. What happens to conductivity above the glass transition? Is there
No, above the in supercooled state, above glass transitions, there will be some liquid-like behavior mostly. So the conductivity can be described by Vogel-Pulcher-Thummam rule. This is not Arrhenius.
Just like viscosity.
Yeah. Yeah. It can decrease also.
It's like a VTF equation.
VTF. Yeah.
Okay.
Even some people have tried to bridge this one from that side, and to calculate the parameter and to understand the process.
Yeah.
Anna has tried this.
Thank you, Professor. Have you been some experience with electrical conductivity changing with microstructure in a dynamically changing system?
Yeah.
Going to high temperatures, for example. Do you have some experience on this?
In the high frequency range or high?
No. For example, increasing the temperature and measuring electrical conductivity during this changing microstructure. Yes, for example, during sintering.
Oh, during sintering. Yeah, if there is some change in
phase
microstructure.
transformation.
Its dynamic process is strongly dependent on that. Because during sintering, you have practically changing the structure.
Yeah.
So it will be strongly dependent.
Don't you have any experience?
No, I have no experience.
Okay.
But theoretically, I can say that it should change.